Okay, I think we'll make a start then. Um, Hello, everyone. Thanks for coming. This is the start of our how-to series. Today we'll be focusing on AutoCAD. We created this series because we got a lot of interest from a lot of students about some software packages that they might not know too well. And we thought that during our courses at university, we haven't explicitly gone through tutorials on these software packages, and we thought it'd be a good idea to definitely run through them in more detail, especially in, I know, 4th years in civil design. This will be very useful for you guys, with space gas next week as well. So yeah, today's session is going to be run by Dr. Joe Gaddis. So everyone please, we'll thank him at the end, but everyone please appreciate Joe taking the time out of his life. And I will give a disclaimer that we will be recording this, so if anyone has to go, or for the people that can't be here today, we will record it and we'll post the link up later. But also keep in mind that anything you jump in and ask a question for will be recorded, so keep it appropriate. But yeah, feel free to jump in and ask a question. I'm sure Joe doesn't mind. But yeah, we'll pass over to Joe to take it away. Thanks, Joe.
Yeah, great. Thanks, CESA, and hopefully my audio is coming through okay there. If you could all just hit thumbs up or yes, if you can hear me. Okay, fantastic. So, look, thanks for the introduction, and honestly, it's a pleasure to be here. As most of you probably know, or those of you at least who I've taught in 3rd year, I'm a pretty big fan of software and computation in civil engineering, and particularly in structural engineering. And CAD, or ability to do technical drawings, is really, to me, a fundamental skill and one that you really should be encouraged to try and develop. So I think the software masterclass is a great idea, and hopefully my lecture today will be of interest to you. And I guess it's equal parts trying to sort of inspire or motivate you to pursue a little bit of self-learning and develop this skill. And also a little bit of the other half will be really around where to get started. So if you're totally new to AutoCAD, you've never used it before, when we get to it in the back half of this lecture, it's really going to be pitched at you, and this lecture will contain everything you need to get up and running with the basics. So just maybe a quick show of hands in the voting tools there. Have most of you 3rd or 4th years, or have I taught most of you before? Maybe yes if I have, or if you're younger students, 1st or 2nd year, or you've somehow avoided my courses, a no. Mostly 3rd and 4th year, but welcome if there are younger students there. So my name is Joe Gaddis, I'm a senior lecturer, and my expertise is in parametric and generative design, particularly in parametric geometry. So this is our latest structure that we built last year. It is not modeled as a conventional structure. It uses quite advanced parametric and generative algorithms to generate the CAD or drawings for these files. They are then ported straight to the machine. So we actually circumvent a lot of the technical drawing that I'm about to talk about in this lecture, which isn't super helpful, but it does mean that in terms of geometric modeling, I'm probably one of the most capable academics in the school. And certainly in my research portfolio, we try to push the bounds of what is accepted practice in terms of geometric modeling for structures in particular. I guess my second qualification is that I am a UQ graduate, and I remember sitting in civil design many years ago and griping openly that I was not taught CAD and we were not at that time allowed to use CAD for our design submission. At the time we were told pretty pointedly by the academic, who I won't name because they still teach here, that sketching was key. Sketches were fine for a civil design submission. I remember being very skeptical of this information, but then having worked in industry for a short time, and then now with a longer career as a professional engineer, sketching is still key. So sketching and technical drawing are really two sides of the same coin, and you should be working to develop both. And a lot of what I'm talking about is relevant to both. So if you're struggling using a specific software like AutoCAD, you could still practice some of the techniques that I'm about to talk about just with simple hand sketches, and that's also really good training for your future professional engineer. So the first part, I'm just going to talk about these two things, and we're going to get to the software in a little bit more detail. So starting with sketching, where does it sit in the design process? We are, as a profession, often visual communicators. We need our sketches as an instant tool for us to, and there's nothing faster, right? Even myself, as a highly skilled parametric model, highly skilled geometer, I cannot communicate more quickly using a software package than I can with pens and paper. So it is really the workhorse of an engineer's toolbox. And it's actually quite informative. So there are a lot of circumstances where, as a professional engineer, your sketches will actually constitute your advice to your client, particularly in early stages of design. There are some really, I guess, key terminology for you to know about. And these are the, I guess, the typical ways that you'll be sketching things. So isometric, which is your bog standard 3D view, but all axes are even, so that the 3D view kind of allows you to dimension things accurately. There's an axonometric drawing, which is more of a it's a different angle, but for structural engineering or engineering in general, it's not as common a projection. And then the final one is orthographic, and this is really, the main conventional drawing. So top, front, and side views with then additional call-outs for 3D views, sections, and so on. So orthographic still is the main 2D drawing convention and projection type we need to engage with. But then outside projections, there's many perspective types, and for sketching, often these are useful as well because they give you, I guess, a more natural feeling for a structure. And 1-point, 2-point, and 3-point perspective types are the conventional ones, but 1 and 2 are probably the main ones. 1 and 2 are probably the main ones. 3, it's getting pretty advanced at that stage. And I guess conceptually, you can consider these as different eye levels, giving you a different insight into angles in the structure, or angles when you look at a particular structure. So I don't know how many of you actively practice your sketching. All right, a quick show of hands at the moment. For those watching, there's about 40 of you. Have you actually sat down with a pen and paper and tried to sketch an object? Not a person. I'm not talking about drawings or landscapes. I just mean sketch a fairly simple object. Okay, so there's only a few yeses there, which means I'm thinking that most of you really haven't necessarily thought about this as a skill that you can practice. But I'm telling you right now, this is really one of the main things that you can work to develop that will impress someone in a design office. There's an artificial hierarchy in engineering offices where someone who is an incredible sketcher or able to communicate very clearly and concisely in terms of their line work or line style, there's an artificial prestige attached to that because it's an impressive skill. It's difficult to communicate the importance of it if you haven't been sitting in a design office context, but I cannot emphasize enough that anytime you spend, developing a simple ability to sketch rectangular or slightly modified cuboid objects, it will help you directly in your career as an engineer. This is one exercise that I use. I wasn't a particularly good sketcher. I'm still not a great sketcher, but I do practice a lot. As a good way to help develop that skill. You sketch a cube as an isometric drawing. There's one on the left perspective, the one on the right is an isometric. I mostly do isometric. You sketch it in isometric and then you decompose it. Right? You just try to use that cube to kind of inspire different types of structures, different types of shadings that you might want to play with, just as a really easy way to practice starting to draw 3D objects. The good thing about starting with the cube then is as you decompose it, you're only really drawing lines in 3 ways: vertical, horizontal in direction 1, or horizontal in direction 2. That's also a really good book, which is really designed to train people in improved sketching. So there's a few terms here. I'm not going to spend a lot of time on this, but things that will crop up in terminology: line styles, color thickness, continuity, dot dash, the things you can pay attention to. Dimensioning in terms of callouts, arrows. Again, it doesn't really matter what style you use as long as it's consistent. Shading and color, because sketches are often informal, you can add these to kind of highlight a feature or draw attention to a feature. When we get to technical drawing, it's a little bit different. It is a more formal communication method. When you section things, you've probably seen in drawings, people cross-hatch or draw a break line to kind of indicate say a symmetric breakpoint or a cut in the structure. And then text and titles, often in all capitals, but the only really golden rule, none of this is all just stylistic, do what you want. The only golden rule is that if you're using this as a communication avenue as an engineer, you need to date, time, and author your sketch. So everything that you produce, if you're intending it as an email or a piece of professional or semi-professional communication, they need to have those three attributes to ensure it's trackable, right, and allow people to refer to a particular document. Particularly in an office context, they might go further and they might actually number a sketch with a project ID and then a sub-reference. That's excessive for your personal use. A couple of examples there, so you can see some line styles. I've got a thin black line and a dot dash line to sort of indicate a hinge point. I've got some annotation to mark common points in the structure as it folds. I've got a crosshatch to denote the cross-section or a sectional view of an element. One thing that kind of surprised me when I started working is that a lot of architects also bring tracing paper. So they will often iterate a drawing not by annotating the drawing itself, but by overlaying tracing paper. And then that will inform the basis of their actual professional technical drawing. So this tracing paper overlay with a different color pen, and you can see I've added some dimensions and callouts with additional annotation there. Again though, for sketching, there's no hard rules, it's whatever is a natural style. But date, name. All right, so I know I kind of tricked you because I said this was an AutoCAD class and I've just given you a 10-minute lecture on, a 15-minute lecture on sketching, but it's a progression, right? So when you're progressing your design past a certain level, things are fixed enough that you can now take the time to draft them properly, right? And technical drawing is the professional graphical communication standard, which lays these down in a computational software. It is typically done later in the design process, so no one will be cutting anything straight up. They'll wait for some sketches or wait for some initial design meetings. But once the technical drawings are started, they're revised. So most technical drawings will be heavily iterated. You'll have revision A through F as the project progresses, and the revision numbers are tracked very carefully as well. The conventions, I just mentioned for sketching, they're quite informal. They're much stricter for technical drawings. I've linked to 2 convention guides here. You'll see that they're like 80-page documents. They're really substantial. They're quite detailed and they lay out specific font sizes, line weights, features, or even cross-hatch textures that have to be applied to different types of materials. For example, road base versus some other types of soil. And they're really designed for professional draftspersons. So as students learning the process, don't push yourself to follow a published convention guide because it's just a huge learning curve, right? Simply worry about initially learning the software and then slowly building up your own sort of style to get comfortable with line weights, texts, font sizes, and some of those basic stylistic features that you can control in the software package. The reason that these conventions are so strict or strongly adhered to is that they're the legal record, right? When you sign a contract, when you're paid as an engineer, you're delivering drawings. That's the outcome of your design advice. It's the legal record. Obviously, your emails, other written communication can still be considered design advice, reports, and so on. Certainly for projects or construction processes, the drawings are number one. And the drawings typically trump other verbal advice, or they have to, there's a lot of work to ensure that what your drawings contain in terms of information is consistent with everything else you've been telling the client on the design project. A last note on this, to make it complicated, companies have their own conventions, right? So in-house, a company, they'll have their own templates, their own conventions. They'll all be similar, but everyone will have their own recipe for how they, as a corporate entity or as an engineering practice, like to present their information, what their standard graphical communication is. A few examples, and you can see the step up from the sketch already. So you've got grids corresponding to certain labeled parts of your structure. Everything is presented at a specific scale. So the sketches, I'm not worried about scale particularly, but scale is critical for technical drawings. You've got a title block over here, which will contain your company number, project name, and then the record of who drew it, when, and what revision. And then there's a huge amount of information contained in the drawing itself with the call outs to all the specific objects. That was an orthographic section view. This isometric views, not as common in engineering. This is an architectural technical drawing set. But in terms of client communication, isometric views and 3D models are really helpful because they're a much more natural way for someone to try to see the information contained in some of these technical drawings. But this is really what a typical engineering technical drawing starts to look like, right? This is a standard precast concrete barrier fabrication detail from TMR, the Department of Transport and Main Roads. It's available on that link 3 slides ago. And interpreting the information on this sheet would take an experienced engineer a good half hour if they weren't familiar with the project. If they're familiar with the project, or they're familiar with this type of structure, they can probably pass the critical details, in 5 minutes or less, understanding that, a lot of these notes are kind of standard notes, or they're not necessarily going to contain information that's unexpected, and same with some of these details. But if we just start to step through some of what's contained here, and just to show the link to what I just explained, so you've got an elevation view. That's a type of orthographic projection. You have these section callouts, which give you a cross section of the barrier there. And these are just your typical concrete barriers you see down the side of a highway. And once you know that, then you can actually try to make sense a little bit more of what you're looking at, because you've kind of got the object in your head. You can see the base, you can see the segments, you can see the sort of ties, how they go together. Within the section then, you get to a detail view. So that callout is a detail here. That shows just that bottom toe. And again, you can see the step change in scale here. We're going from a 7:50 down to sort of a 10mm scale. And then there's further detail callouts and section kind of iteratively. And then there's also a few standard diagrams there. This is then the reinforcement schedule, which again is quite meaty in terms of the information that it contains, but it contains all the information you need to fully fabricate this concrete barrier. So it's quite an excellent technical drawing. It's very informative, but you can see how something like this is only going to evolve iteratively over a project's lifetime. It's going to start off with some key sketches, some reinforcement detail will be filled in, the draftsperson will start to arrange the information on the sheet, and some items will be tuned or refined, and then more information will be added as the design progresses, and then finally, your tables and notes will be dropped in, which provide the complete documentation of any assumptions or limitations in the design advice. So that's not to try to put you off from learning CAD, it's just to kind of contextualize the spectrum that exists from hand sketching through to being a full-blown technical draftsperson. Right? As an engineer, you couldn't necessarily be a technical draftsperson. There are some practices where engineers do their own drawings, most don't. But the point is that throughout that entire spectrum, you can work to improve your orthographic projections, to improve your sketching, to improve your base level of technical drawing so that you can measure or modify objects off a technical drawing. And then just increase your familiarity with graphical communication. Right? Because as an engineer, you're responsible for this information. You have to be the one who understands everything on the page if this was your project. So, are there any questions so far? All right. So this is kind of a summary of the overall process. If you're an engineer sitting in an office, you develop a base design. Typically, this is sketches or just a simple graphical representation. The draftsperson in the office will prepare the drawings, an initial pass of the drawings. Then that will be iterated. So the engineer will review the drawings and revise the design with the client. The drawings will be updated. that process will repeat, and at some final stage there'll be a final approval and sign off, and that's the end of the project. All the drawings are handed over to another a contractor or a fabricator to then progress through their internal processes. Hopefully that all makes sense, but what I've got here is kind of a case study to illustrate that. So just in a microcosm. So pause for a second. I'm just going to ask a question. Have any of you heard of the Vivid Light Festival in Sydney? Use the voting buttons to let me know. So the Vivid Light Festival is a really amazing event. I've never been there, but it's kind of on my bucket list. Been pushed back a little bit because of current travel restrictions. But basically, Sydney just converts itself to a giant outdoor lighting event. I think you should all be able to see my internet there. So the Opera House is lit up. There's a number of individual public exhibitions, which could be invited from sponsored companies, or companies can submit a design which is accepted, and it's set up all throughout the city and people can walk through and see all the stuff. It's pretty cool. But there's one project that I'm about to show you. Oh, just turn the audio off here. It's a group called Emergence. It's not an engineering firm because engineers tend to stick to normal punctuation, so that will be an architecture and design firm. But what you're looking at is a giant foam head. It's manufactured and then set up with projectors so that the people, anyone attending the festival could come, scan their face, have it projected onto this giant head. And then there are a number of general patterns that will be projected onto it, such as this sort of faceted video here. So I don't know if any of you are familiar with projection mapping as an interactive light event, given that most of you didn't look like you're familiar with Vivid. I'm assuming you're not that familiar with projection mapping, but basically you just set up projectors to warp a geometry such that when they're projected to a 3D surface, you get a 3D object. Anyway, that's just the background. The point of this is, what does that look like to the engineer? So what I've got here, I'm not going to go through it in great detail because I do want to get to AutoCAD at some point today. But it's distributed in a link that CESA can send you, but it's basically the design brief that was presented to NPM Consulting. Some of you might have seen Simon in civil structural design, Civil 3350. He sponsors the Structural Design Award, or his company sponsors the Structural Design Award, and he was the engineer for this project. But they're approached by the company and asked to design a base connection so that the head could be set up without blowing away, right? An engineering problem. So the head's pretty big. It's about 1.8 meters high, 2 by 2 meters. It's got to be dropped down. Everything's transported down by a few guys in a small truck, and they've only got half a day to set it up. So they're the constraints given to the engineer, and the engineer then has to determine, well, what performance is required, what is the potential solution, and this is the information they're given. So this is a image of how the projections are set up. And then this is the only image provided, the only technical image that you could consider that was provided to the engineer as to their constraints. So this is the outline of the head. This is an internal void that's manufactured during the foam process. So what I'm going to show you isn't so much how the engineer designed this, that's a separate question, but it's what does that design progression look like from sketching through to technical drawing. So the first response from the structural engineer is something like this, right? They've literally just photocopied that information, doodled over the top of it, a couple of colored pans, section, you know, it's neat, but it's definitely a sketch. And then they've done a separate sketch on a bit of graphics paper, and they've photocopied that and stuck it on the sheet as well. They've photocopied on a drawing block, which contains a couple of bits of information, but the key ones, you remember I said, was the name, date, some identifying feature, and then that's a hand sketch. And that starts the design process. That is enough to talk to the client, get things rolling, see if they're heading in the right direction. The design basically hides ballast inside the head to weigh it down so it can't blow away. The draftsperson does a neater version of that, which constitutes either a formal version of that sketch or a vision A of the technical drawing, depending on how you count. And then the client doesn't like it, right? The client doesn't want that screw detail. This is basically a plywood plate that's screwed along the outside. The client doesn't want that visible outside of the head. And they don't want a cross joint in the plywood. So what has to happen is the design's updated so that there's an internal plywood base, and there's basically a staple detail which is inserted here. And what you can see is that the technical drawing has been sketched over to add all these features, right? So the notes have been added, a detail has been added. Some of the features which were already in there have now been redone based on an updated design, which is iterated with the client here. The engineer then reviews it, and the green basically is a fairly common process. If you've got to review this whole drawing, they're highlighting all the information which is okay, and they're showing in red all of the information which still needs to be changed. So this is an internal communication between the engineer and the draftsperson, and you can see the level of detail, right? Everything on this drawing is reviewed and approved, right down to spelling, grammar, missing technical information. And that's the final drawing, right? So that's the end outcome of that entire design process, and that's the end of the project as presented to the client. So does that all make sense? It's a strange example, but it's a really good one to just kind of contextualize, you know, realistically, what are we talking about here? The skills that we're talking about, it's not learn AutoCAD or learn how to sketch, it's learning how to graphically communicate as an engineer. And you transition very naturally from one to the other or between them, and you'll need to use both of those skills together to be an effective engineer. So, moving right along, I've burnt half my time and I still haven't introduced you to AutoCAD, so this is a bit of a terrible software masterclass from that perspective, so let's get on with it. Do many of you know what you're looking at here? This is one of the original drawings. It is a technical drawing, but it was done before AutoCAD of the Sydney Opera House. Top-down view. You can look at the full set of technical drawings here, but these are what won the competition and ultimately led to that project being delivered. The drawings are just beautiful things, as a lot of high-end technical drawings really are. Technical drawing or AutoCAD, it's not new. It's really, really, really old. It's actually upsettingly old if you consider the amount of CAD that's taught in your curriculum, and this is a 55 years old process. It's actually older than, you know, things like computational direct systems method and finite element analysis. CAD has been around for longer. The initial invention, if you look at the video of the first demonstration of a CAD package ever developed by Ivan Sutherland, this is from 1963, the terminology and the functionality is eerily close to what we still use today. So this video talks about points, it talks about snapping, it talks about lines and geometric primitives. The thing that's different is the hardware. So you can see that their light pen and the computer driving this thing is a little bit different to the computers that they're using, but the actual terminology is sound, right? I would more or less got it right first time. But having said that, there are features that have been added as computational power has been upgraded. So when we talk about CAD, you've kind of got to be careful as to what that does and doesn't mean. So broadly, modern CAD software, or computer-aided design or computer-aided drawing, I'd classify its capability as 2D modeling, where you're just drawing things in 2 dimensions, but that's perfectly fine for a lot of technical drawing, particularly for, say, orthographic projections. There's 3D modeling, where you're actually representing things in 3 dimensions. So there's some of those isometric projections I showed you. There's rendering, where you're actually adding a lot more textures and material-based effects. Not so relevant to engineering, particularly structural engineering, highly relevant to architecture. And then there's parametric modeling, which is my jam, but it's essentially a variable control over all of these objects. So it's essentially a programmatic approach to these types of modeling strategies. That's CAD. There's a whole bunch of other computer-aided X things that also exist. So computer-aided engineering, all of your performance analysis softwares. Computer-aided manufacture is what they typically learn in mechanical engineering, but it's also used by fabricators for shop drawing integration in the construction industry. So that's basically drawings or models are designed to interact directly with the manufacturing process. A subset of CAD packages are specifically designed for the building industry. So they are AEC softwares, but there's more or less 100% overlap now between AEC and CAD. Every CAD package will have an inbuilt construction capability, so you don't need to worry too much specifically about this one. And of course, BIM. BIM is really, I guess, the modern extension of CAD, where they're trying to embed a lot of additional information, not just geometry, but all sorts of information for building into the model. And so a lot of draftspersons have now become, I guess, expanded in their professional role to BIM technicians. And a lot of engineers have also become BIM technicians or BIM consultants, because once you operate at this level of model development, it's not simply about a technical drawing, it's really about developing a model that is as true to life as possible. It requires quite a high level of software proficiency and quite a high level of design proficiency. You do learn BIM in your construction management courses. I would say that it's much easier to learn if you have a basic CAD understanding, and many of these processes are. All of these start with CAD, and all of CAD starts with the simple 2D modeling. These are the common packages that I see talking to industry. The ones we're going to talk about now are Autodesk and AutoCAD and SketchUp. They're both free for students, and they both have awesome online tutorials for people who have literally zero experience. AutoCAD is a really common AEC one, particularly at, I guess, smaller and medium practices. Rhino 6 is an extremely popular tool because it integrates really well with parametric modeling. It's not free, but it's very cheap. So AutoCAD is free because it's much more expensive as a paid subscription. Rhino is not free, but it's a cheap paid subscription for life. So that's kind of the trade-off. I mostly use Rhino 6, but these two are very, very similar. If you learn AutoCAD, you can be fairly confident operating Rhino 6 really with maybe 1 hour turnover to figure out the slightly different buttons, and vice versa. Creo is something that some of you might have used in high school manual arts types of courses. I've never seen it used in an engineering practice, but again, it's transferable skills. So if you've picked up 2D, 3D modeling and something like this, a lot of the terminology I'm about to talk about will be familiar to you. So having said that, let's actually jump into this damn software. So this is AutoCAD's official guide for how to get started. Pull it up here. Okay, so this is what we're going to spend the rest of today's session on. Basically, just really basic how to get up and running in AutoCAD. So On the left here, let me just maximize that for a moment. This is AutoCAD 2021 student version. If you sign up for an educational license with Autodesk, you get access to most of their softwares, and most of them are fully fledged, so there's no reduction in functionality, which is awesome. Then on the right, over here, this is that link that I just had in the PowerPoint slides, and it's AutoCAD's official getting started guide. And it's really, really informative. It hasn't got a lot of the kind of annoying YouTube-esque, here's how to learn a thing commentaries. It's just bare bones and professional. The four that I'm about to walk through are these four here. So the basics, how to view, how to draw basic geometry, and then how to check precision. I would consider those four more than sufficient to pretty much draw some useful things, up to and including some of the designs you might be sketching for some of your courses. You'll have to though then progress in your own time to get to a point where you might be able to produce, say, a drawing block. So if you work through some of these layers and properties, and particularly through the layout and annotation, this is what will get your geometry onto a drawing and looking kind of neat. But there's heaps of templates and heaps of advice. So if I get you up and running here, you should be able to work through the rest of that yourselves in a pretty short time. We're really only talking an hour or two, or half a day at most, if you really have to wait for the download to install. So starting with the basics, and hopefully that's all coming through pretty clear. I'm not sure how pinched your screens are, but what I'm going to try to do is keep the Autodesk page open on the right, and then show you the relevant buttons on the left in the software. But just give me a shout if that's not clear. There we go. Okay. All right, so you'll open AutoCAD and you'll get a screen that contains a whole bunch of information here. Just ignore that. Just click New, this top left button up here, same as Microsoft Word. It will ask you to select a template. I'll talk more about that in a moment, but just whatever's fine. And this brings up the base screen. All right, this is you piloting AutoCAD. So if you look very closely, you've got a grid here. So you can change the colors, but it's gray on black, which is kind of good for the eyes. You've got a zoom wheel and you've got some drawing functionality here. So we're going to step through everything on this screen. But what you've got is a command window, toolbar, navigation tools. When you opened a template, you already made some assumptions about the units. So if you type in units to this command line, it will show you what system that your template is now operating in. It's operating in millimeters, degrees, with that level of precision. You can change that if you like, but millimeters is fine. I'm just going to draw an object. I'll show you how to do this in more detail later, but this is just going to give me something to show you the view tools. Okay. So once you start drawing things, or even before you start drawing things, you need to be able to navigate the viewport. One of the main problems that I have when I'm trying to draw CAD is I'll start using the software. I'll type in a number, which I think would be good, something that's 30 meters long, and then it doesn't look like I've done anything because I'm operating in units that are inappropriate. So I thought I drew something that was 30 meters long. I've drawn something that was 30 millimeters long, and I'm zoomed out to a scale of meters, right? So number one frustration that you'll encounter trying to use these softwares is just a mismatch between the units that the software is set up to deliver and what you're actually trying to do. So related to that is this issue of zooming. So you've seen that I've just zoomed in and out on the object because I knew where it was. There's no way I'll be able to find that without knowing a bit more about zoom tools. So just delete that and show you this. So when AutoCAD starts, you're operating in a top view and you're operating in a 2D wireframe view. This little button up here allows you to step between different styles, I typically operate in a 2D wireframe or a hidden, a 2D wireframe or a conceptual, because it gives you just a good base feeling for 3D objects. Then what this tool over here does, it's similar to Space Gas if you piloted that, but basically you can click to constrain yourself to different views. So top, right elevation, front elevation, left elevation. It's a cylinder, so they all look the same. But then if you click the quarters, you constrain yourself to your isometrics. And again, this is why I wanted to just introduce some base terms like isometric and orthographic projection, because it's really fundamental simply to looking at your model. If you click on this top left component here, you can see top, bottom, left, right, front, back, plus your usual isometrics. So the orthographic projections and the isometric projections, you know, they're going to cover 95% of cases of things that you're actually drawing. If you really want to freestyle and click around, you can hold various combinations of shift and control to rotate space, zoom, and pan. So they're all sort of described here in the AutoCAD guide, but you can additionally use these features here to jump between them, or this one here. Oops. So when you set up a new drawing, as I've already mentioned, oops, it'll open in a 2D top view, so the XY plane is inside. You can dimension the object that you've just drawn, doing a particularly good job of it. That will show up in the units that you're using. A surefire way to tell if you've opened the wrong template is if your units are in feet and inches. You can change it in the units command, or you can just simply open a new template that's already in the right format. AutoCAD ISO, the default, that's a default metric unit template. That's probably all you need. Don't worry about creating your own template. Don't worry too much about format and precision. You can figure that out later. That's not going to stop you getting up and running. But that's done. Like I said, these things, they're really straightforward. You can punch through them each in about 5–10 minutes. So, view. I just mentioned briefly the mouse tools. Oh God. I basically covered everything that you need there. A few other ones that I find super useful are zoom. I'm typing in zoom to the command window here. And when zoom comes up, you can zoom around all, object, or extent. If you zoom all, it will zoom in only on everything in your, I'll show you a couple objects here to show you the difference. So I zoom, and then I can either click all or type A. It will zoom everything in my screen. If I have an object selected, I click an object to select it. I hold down Shift to deselect it. And if you look very closely at my cursor, you can see that it has a plus sign if it wants to add something to my selection, or a minus sign when I hold Shift if it wants to take something out of my selection. But if I now zoom my object, it's just zoomed into that one item there. It will also rotate about that one item. So that's very useful if you're trying to look at some detailed features. But again, for your current stage, I just recommend that you keep using zoom all if you lose your objects. If you accidentally zoom out here and zoom in over here, and you're trying to figure out where your line work is, this is something that will happen to you all multiple times. Just take a breath, select everything, Control A, zoom, all, and all as well. It shows you where the objects you're actually drawing are in your model space. So that's the reason that basics and view are first. They're more important even than geometry, because once you start drawing things, you're going to lose them straight away if you're not actually able to navigate your model space here. But the navigation tools are very easy. Use your mouse, use this dial, and then use zoom. Great. Next, geometry. Let's start drawing something. 3D is too advanced. I'm just going to go back to 2D, start fresh. And I don't say that in a condescending way at all. I would honestly just start drawing in 2 dimensions. If you're new to CAD, it's great. And you're going to pick up a lot of the basics pretty well. So these are about in order of use. Line, click, click, enter when you're done, circle, click, click, you're done. And you can drop down to look at different ways of creating some of those objects, or dropped out your callouts to find different types of features there. Now, that's fine, but as engineers, you want to draw something fairly precise. This is going to start to overlap a little bit with the next section, but you'll notice here that when I click, I can specify my first point. And if this, see that little number highlighted in blue? That means that I can actually type numbers in there. So I can specify my first point at 0, 0. And that means that I'm actually drawing now from the origin. So I can input my points, then I can input my length. So the same way, I want to draw a line that's 3 meters long, which is 3,000 millimeters. I can constrain it to an exact length by typing in that number and hitting enter. But that's drawn it in the direction that my mouse was pointed. I can, oops. I can constrain both the length and the angle. So I want to draw a 3 meter line at 0 degrees to the horizontal. That's how you start to input things exactly. I'll talk more about that in a moment. There's faster ways to do that with snaps, but I'll get to that in a second. What you'll start to see here is that as you're typing in dimensions exactly, you're constraining yourself to a grid. So the grid here with grid settings will allow you to only draw objects at specific points. So going from 0, 0 to say 1000. So let me just draw the rectangle here. Okay, so this is exactly 1 meter long, and I did that by turning on snap mode. So for most of your objects, you don't need decimal precision, you just need it closer to 1 millimeter or 10 millimeter. Snap mode allows you to use the grid to draw things pretty quickly. Turn it on there or hit F. That just gives you a slightly more rational starting point, like so, okay? But of course, you can just select your objects and type in what they're meant to be. 250 wide, tab, 15 meters high, tab. That's now a rectangle of that exact size. So I will rarely ever just click around the screen. If I do, I'll make sure I have my snaps turned on, which I'll talk about in a moment. I typically start a drawing by exactly inputting my coordinates and where I want them to go. So that's a 2400 by 1200 sheet. That's how I start most of my CAD. Circles, fine. Polylines are just lots of lines joined together. The difference is if you draw a polyline and select it, you select everything at once. If you draw a bunch of lines and select it, you select one at a time. It's not that exciting. If you join your lines together, you get a polyline. So that's pretty trivial. Not that relevant if you get started on drawing stuff. Hatching is pretty advanced and not that relevant to structural engineers, so don't worry too much about it. Great. Final thing I'm going to talk about, and this is the most important thing after the units. Precision. So as I just mentioned, if you just start dropping in lines around the place, you're going to lose track of what things are meant to be. AutoCAD has a bunch of really powerful tools to help you draw precisely, and you can see that your first drawing object, the first piece of information on the screen, allows you to exactly specify the point and where it needs to go, X, Y coordinate. The first tools in your model space, your grid, and then your snaps are designed to help you draw things in a more controlled way. So they're really here to try to help make your drawing precise and accurate. So the thing I just mentioned about lengths, so I'm going to draw a line at 100 and then 45 degrees. That's called polar tracking. That's the main one that AutoCAD likes to use. The next one, and this is the most important part of my entire lecture, it will transform your ability to use CAD, is object snaps. So when you start CAD, you might have snaps turned off. So as you float around the screen, you know, maybe you can snap to the grid, maybe you can't, but it's not giving you any useful references to the objects that are already there. When you turn on your object snapping, it will allow you to jump to certain key features. So I want to draw a line or a rectangle, whatever I've clicked, from the start of this line. If you right click on object snap and then open the settings, these are all the things that you can jump to. You can jump to the midpoint of a line, you can jump to a node, a quadrant of a circle, an intersection, a tangent, or parallel. The reason these aren't all turned on is because once they're all on, you've got a huge amount of snap points that your cursor will jump between. You can turn them on or off to match the object that you want. So I want a circle here, and I want a line from the midpoint of this line to the tangent of this line. And you can see that they're all color coded to help you select the right thing. And they're all snapped to when you get close. Center, tangent, like so, endpoint, midpoint, endpoint, tangent, center, that, midpoint. So that's not anything in particular, but the point is that you can quickly create very precise geometry. That is exactly halfway between here and here. This is at exactly the tangent point. This is at exactly the endpoint. So it's the best way by far to get precision in your geometry. And it means that if you're starting to do something like, say, a reinforcing structure or a simple steel structure, you can be confident that all of your lines are precisely drawn. The ends match the ends. If you're drawing something in the middle or trying to reflect it about the middle, it's all lining up nicely. So I'd recommend using a lot of time playing with these snaps. Turn them on or off, see what it does. Same with the grid. And then, you know, just drawing some basic objects to build up your familiarity. There's one other point here that you might have seen just as my cursor jumped around. It will already try, as well as the snaps, it'll have these guidelines. So it will try to help you match things up. So it's trying to keep it horizontal with this line and then vertical with this line. So this is a parallel rectangle. Using the guides is much easier than trying to just guess this in space, because if I try to guess where the end of this point over here is, it won't work. If I try to match the guides up, it works really well. So use your guides, or they call it snap tracking. Use your O snaps, use your grid snaps while you're getting up and running. And I would strongly recommend just starting in 2D. 2D top view, 2D wireframe, working with your 2D geometric objects. It's a perfectly sound way to get up and running with CAD, and it will allow you already to start drawing a lot of objects towards your first fully fledged technical drawing. All right, so just to wrap everything up, slideshow from current slide. So this is an exercise I'd recommend you do. Just pick something and draw in 2D orthographic. Don't worry about 3D. Don't worry about, you know, developing complete technical drawing. Start with a sketch, then transfer that to CAD, but practice your precision. Then, if you're confident with the overall object, maybe work on a small detail, so some particular feature of it, as if you're zooming in. And that's all the information that you need to place on a technical drawing block and give yourself a bit of practice with that, but we didn't have time to cover that today. My examples are not creative, they're inspired by the desk in front of me, but things like your computer monitor and desk, things which are kind of rectangular, I'd recommend is a good place to start. Things like with curves, particularly more complex geometry, they're pretty hard. So I wouldn't jump to that, and particularly things like a computer mouse, that's actually a modeling requirement beyond what most engineers are going to need for most of their profession. You saw with the NPM consulting example with the foam head, there's no attempt to draw the head, they just need the base outline. The last thing is the 3D modeling. I didn't talk about it, but in the files I've sent CESA, which they can send you, there's a nice example of just getting up and running with SketchUp. Basically, this is the strong floor in the AEB structures lab. So if you've walked into the AEB UQ, look down, this is a big old concrete block. This drawing has dimensions on it. And there is also a brief example with a solution. Here, there, which shows you basically the steps to model that in 3D in SketchUp. But it has this caveat, which I'd say for all CAD, there is no particular way to correctly model something. There's infinite ways to model any object you're given. The only choice of steps is what tools you're familiar with. If you're only familiar with rectangles and lines, that's enough for you to model this object. If you're familiar with cubes, arrays, extrusions, that will help speed up the modeling process in 3D, but it's not something that means that one way is more correct than the other. I think that's about it for me. So there's a little bit more website on my stuff here, although it's a bit sparse at the moment because it's down for maintenance. This is a photo of a structure that we generated through some of our CAD algorithms, but basically we could fabricate a house in Papua New Guinea from our CAD packages. It's parametric, it's cheating, but it's all just a 2D drawing which is sent to a machine which cuts the files. So the skill set for you to produce something like this is the exact one I've just described, or at least the start of it is. Okay, that is all from me. Happy to answer questions, or otherwise thank you for listening. Oh yeah, great question from Bella just on dimensioning. That is a pretty key feature. So it is included in the AutoCAD Hitchhiker's Guide, but just to show you quickly, this is a object. This is the annotation tool. So you can add a whole bunch of dimensions. You can add it by object, so it's selected the entire line, or you can add it by endpoint, here to here. The one catch with dimensions is the size of them. It will be linked to your template. So you can see here that I'm drawing in a dimensional template, but the scale of this is not appropriate to the font size. So this is an 862 meter long thing, and that's probably like a 12 mil high font. So the fonts are drawn exactly to relative scale. If you want them to adjust, you'll have to draw an object at an appropriate scale or adjust your template and annotation size. I don't know how to do that directly, but it'll be in these settings somewhere. The lecture, the question from Cedric, I might let CESA answer that, but no, at the moment there isn't really a strong course inclusion for developing drawing skills like that. I definitely recommend that there was something you can sort of develop as a co-curriculum, particularly for CV stacking. So a lot of my students who've come through my thesis or master's course, where we do look at Rhino and Grasshopper in depth, that proficiency in that software has been remarked upon in job interviews, and similarly your experience with Space Gas and some of the other analysis packages that you're using in your courses, things like that are really good to kind of include on your CV or work to develop so that you can confidently say you can use it to prospective employers. Thank you very much.
Thank you, Joe. I think I speak for everyone when I say that we've never really been taught any of this before, so we really value everything you've just taught us there. So if everyone, I guess, could join me in unmuting their mics and quickly thanking Joe. Give a round of applause.
Thanks, Joe.
Thank you, Joe.
Yeah.
Thanks, Joe.
Everyone.
Thanks, Joe.
Thank you very much.
And before everyone goes, quickly,
Joe.
just like to remind everyone that next week we have at the same time, there's a space gas session. Hopefully everyone's used that before in some courses in some form, so we might be able to progress a bit further. And also, Joe has sent me all these slides, so we will distribute them to everyone, and the lecture is also recorded, so we will be uploading that and distributing that too. Yeah, thanks very much, everyone, and we'll see you next week.
Thanks,
Thank you.
CESA.